Hello everyone. Previously, we always assume that the designs are balanced. In a balanced design, we have an equal number of replication and no missing values. In practice, a balanced design can be difficult to achieve due to a large number of treatments, limited resources, practical constraints, and missing values. So, what can we do if we cannot use a balanced design? These are the aim of this lecture. When we have missing values, we should avoid using 0 to denote these missing values because 0 can be a real response. Let's see some example. In each case, decide whether a 0 is a missing value or not. A 0. Insect damage is the result of the treatments of no insecticide. A missing value. Insect damage is not due to the fertilizer treatment. A 0. Other cows in the same treatment produce very little milk, so 0 milk production is likely due to treatment. A missing value. This cow does not produce milk due to illness, which is unrelated to the treatment. If the experiment design is CRD, the effect of loss on the analysis is minimal. However, because the number of observations is not equal across treatments, when we do a pairwise mean test, we must calculate the standard error of the difference or SED for each pair of treatment. In a blocking design, we can estimate the missing values prior to doing the analysis. This process is also known as imputation. We can also remove the missing values and use the available data to do the analysis. In this case, we might lose a block or treatment. Alternatively, we can use a mixed model approach that can handle unbalanced data. When the number of treatments is large, it is often not possible to have a complete set in each block of an RCBD. In this case, incomplete blocks can be formed. In incomplete block designs, each block contains less than the complete set of treatments. Let's define P is the number of blocks, T is the number of treatment, K is the block size, R the number of times a treatment appears in the experiment, and lambda is the number of times a pair of treatment appears together in the same blocks. An incomplete block design is said to be a balanced incomplete block design, BIBD, if all treatments appear in exactly R times. So the number of experimental units equal to and all treatment pairs appear together in exactly lambda blocks. This setup ensures that each treatment is estimated with the same precision because each pair of treatments occurs together in the same number of blocks. Let's see an example. The number of blocks, the number of treatment, the block size, the number of replications, and the number of a pair of treatments appear together in the same blocks. The skeleton ANOVA for BIBD. The linear model. This skeleton ANOVA and linear model are similar to the one for RCBD. So what are the differences between these two designs? In RCBD, each block contains a complete set of treatments. So the total experimental unit is BT and the total degree of freedom is in BIBD, each block has a size of K, where K is a subset of treatments. So the total experimental unit is BK and the degree of freedoms is BK minus 1. Therefore, RCBD and BIBD also have a different residual degree of freedom. In a factorial experiment with two factors, A and B, the treatments are the complete combination of levels in both factors. The level of factors B have the same meaning under each level of factor A. This is known as a cross design. For example, the effects of N and P fertilizers on potato yield. When factor B is nested in level of factor A, the levels of factor B do not have exactly the same meaning under each level of factor A. This is known as a nested design. In a nested design, the levels of factor B are not identical to each other at different levels of factor A, although they might have the same labels. Let's see an example. A company purchases material from 3 suppliers. The materials comes in 4 batches. In this case, batches are nested within suppliers, as batch 1 from supplier 1 is not the same as batch 1 from supplier 2 and batch 1 from supplier 3. An experiment was conducted to test 2 types of insecticide. Systemic and contact. This experiment tested 2 brands of systemic and 3 brands of contact insecticide. In this case, the brands are nested within the types because the brand of systemic insecticide is not the same as the brands for the context insecticides. For a two-factor experiment that has treatment A with A levels and treatment B with B levels, where treatment B is nested within treatment A and R blocks, the skeleton ANOVA is because factor B is nested within factors A, there are no main effect for factor B, nor the interaction between factors A and B. The linear model we need to replicate the experimental units to measure the experimental error. If we measure the same experimental unit multiple times, these measurements are not a replication because they are not independent. These multiple measures are known as pseudo-replications or subsampling. We cannot use pseudo-replications to estimate the experimental error. Let's see some example. A glasshouse experiment to test the effect of drought on crop flowering time. Each water treatment is applied to a pot. Each pot has multiple plants. The flowering time is recorded for each plant. What are the experimental units in these experiments? The experimental units are the pots. How many replications do we have in this experiment? There are two replications. Each bench is a replication. An experiment to test the effect of diet on milk production in dairy cows. Each diet is applied to 2 cows. The milk production is recorded for each cow. What are the experimental units in this experiment? The experimental units are pair of cows. How many replications do we have in this experiment? There are 2 replications. Each paddock is a replication. If we treat the subsamples as replication, we mistakenly think that we have more replication than we have. Therefore, we increase the degrees of freedom of residuals and likely to reduce the error mean square. Consequently, we also use the wrong error mean square and degrees of freedom for our F statistics. Let's see an example. For a CRD experiment with the number of replication R and the number of treatment T, the skeleton ANOVA, if we take S measurements from each experimental units and mistakenly use these subsamples as replication, the skeleton ANOVA because this is larger than this. If the sum of square of residual is almost the same, the error mean square for the pseudo replication is smaller than what it should be. Therefore, the F statistic from the pseudo replication analysis is overestimated. We can deal with repeated measures by using summary statistics, such as the mean or sum or median of this repeated measure for each experimental unit in the analysis. If we have R replication and T treatments, we expect to have TR observations. For example, for 2 treatments and 2 replication, we should have 4 observations. If we take S measurements for each experimental unit, for example, we take 3 measurements for each experimental unit, we have 12 observations. However, we can calculate the mean of these samples for each experimental unit, and we will have 4 mean values. We can use these mean values in our analysis. Alternatively, we can deal with repeated measure by incorporate these repeated measures in the analysis model. We add another term in the linear model and skeleton ANOVA to account for the effect of subsampling. For an RCBD with R replications and T treatments, where S measurements are taken from each experimental units, the model, the skeleton ANOVA, Let's see an example. The number of treatments is 4. The number of replications is 4. The number of subsampling is 3. We can calculate the mean of these 3 measurements for each plot and use this mean value in the analysis. In this case, the number of total observations equal to the number of experimental units, which is we can use all the measurements and account for the subsampling in the model. In this case, the total number of observations we can use either approach. However, we cannot use the subsampling as replications. A crossover design is a repeated measurement design such that each experimental unit receives different treatment during a different time. In this design, an experimental unit crosses over from one treatment to another during the experiment. For example, most of our experiments are using parallel design. In a parallel design, experimental units are randomized to treatment and remain on that treatment throughout the experiment. For example, a crossover design requires less experimental units because the same experimental units are repeated over time. For example, we want to test the effect of 4 types of diets on the milk production of dairy cows. In a parallel design, we will need 16 cows to have 4 replications. In a crossover design, we only need 4 cows because we can use the same 4 cows in 4 different time periods. The main disadvantage is that the carryover effect may be confounded with treatment effects. A carryover effect is defined as the effect of the treatment from the previous time on the response at the current time. For example, the effect of diet A given to cow 1 in week 1 might confound with the milk production of the same cow when given diet B in week 2. We can overcome this carryover effect by using a lengthy washout period. A washout period is the time between treatment periods. Or we can use a proper crossover design, such as a Latin square design. In a glasshouse experiment, we often concern about microclimate variation in the glasshouse that might affect the responses. One approach that often used to cope with this concern is by rearranging the relative locations of plants in a haphazard manner throughout the experiment. This approach assumes that the effects of microclimate variation are the same throughout the growth stage of the plants. For example, when we haphazardly change the randomization, we assume that the effect of the microclimate are the same during planting, flowering, and grain filling. If this assumption is not true, this could lead to a carryover effect. We also confound the microclimate effect with the treatment effect. The better approach is to use a proper experimental design, such as a row column designs. In this case, we can adjust the variation due to microclimate by fitting the effect of rows and columns. When designing an experiment, keep it as simple as possible. Remember to replicate the experimental units. Now, can you do this?